Okay, so we're looking at the cover screen, and this is Biochar Environmental Research to Real World Project Development. So I'm based in Philomath, Oregon. The name of my company is BioLogical Carbon, and I've been doing this work for about 20 years now, working primarily in the forestry sector is where I get the biomass from, but we've processed all kinds of biomass. I like to build machines, but what I realized was that other people were going to do it, and I started working on product development primarily, probably 8 or 9 years ago, as opposed to just making chars. Let's switch to the next slide. So I've been able to develop quite a partnership of folks, I think, from a couple of aspects. Is I'm pretty straightforward with people about what I know or understand and what I don't understand, and then I go to the experts and start talking to them. And what I did understand about biochar when I first came across it was that we had a chance to enhance low-value biomass utilization, which in the West and all over the country is really getting a lot of eyes on it, right? People are starting to understand at the federal level that we really have to do something with this, and the low-value biomass utilization is getting us kind of in the door when we talk about that, because we talk about creating jobs in a rural environment, we talk about cleaning up the environment, we talk about making biomass energy. All these things are exciting to people. So if we switch to the next slide, I can kind of talk about the general philosophy that I try to approach these problems with. And it's essentially that, a lot of our knowledge is based on cheap energy and fossilized energy, and how our industrial systems developed was based on that. And that simply isn't viable anymore. And we have to move to integrated systems and think more about systematic solves than just basing everything on cheap energy. And so it becomes kind of a design science. Let's go to the next slide. So back in 2009, I started talking with a colleague, friend of mine, Dr. Marcus Klaber over at Oregon State University, and we came up with some specific goals about how to tackle some of these environmental problems that we were seeing around biomass and the great potential about the creation of biochar that we all are kind of aware of, right? So we want to be able to use energy from biomass and ensure that there's no additional carbon released in the atmosphere. We're hopeful that by converting part of this feedstock not into energy but into a stable form of carbon, we will actually sequester carbon through this pathway. And then the materials that we make, the carbons that we harvest, are going to improve soil and water resources by taking advantage of the unique physiochemical properties of these artfully prepared chars. So this was me. This Pathways to Biochar is, just kind of thinking about sustainable systems, right? And the inefficiencies of our food systems, of our energy systems, and kind of churning that over in my head while I was sitting on the back of the boat and trying to come up with a solve. Advance to the next screen. What I came up with was, I read a lot of Buckminster Fuller, I read a lot of E.F. Schumacher, and that in order to solve these problems, that they were going to have to be necessarily local. It was going to require sort of a technological revolution, based on systems, based on integration and turning our wastes into resources. Next slide. So now these are great possibilities to investigate, right? We have food security, energy security, job creation, water cleanup, environmental revitalization, all of these things. And this can lead to this thing that I call the great black panacea, right? It's like, it becomes this religion almost, as Tom Miles has said to me. But we have to investigate this rigorously. We have to investigate this as scientists and come up with, solves that are viable and real world and economic, and it's complex, but it's so great of an opportunity. We should investigate this rigorously. Next slide. So I'm come from the forest sector. There's a huge problems in our forests, as we all know and have all seen over the last several years. And these problems were predicted for decades, right? We knew this was coming, and now it's here, and we have to deal with it. Next slide. I worked as the director of biomass energy for years for a company called Thompson Timber and Starker Forests in Oregon. And basically, they allowed me to do my primary research. So here's a couple of slides of the kind of biomass that we're looking at. So I'm on slide 10 now. I'm going to move to slide 11. There are tens of thousands of tons of biomass just at the log yard where my facility is. Next slide, slide 12. And as we looked at this material, we started investigating ways to make it into biochar. Next slide, 13, the industrial Legos. And this is what I ended up building my initial machine out of. That was the leftover refuse from the milling industry, essentially. I went around and with colleagues, some guys that are better fabricators than me, and we kind of put these things back together. Next slide, slide 14. And in the process, I was talking with Tom Miles, and he helped me source a gasifier that I could use as my thermal drive. And so we go to the next slide, and this gasifier is a fantastic machine. It's what I use to drive my retort. It consumes 100 pounds an hour and puts out about a 500,000 BTU flame. The next slide, I'm going to go through these slides really quick just so you guys can see kind of the history of this project here. And so we started fabricating the pyrolytic retort in February of 2010. Next slide, slide 17. You can see me and my buddy Gary putting it back together from found parts and pieces. Next slide, 18, is just more of the fabrication. And we'll kind of fast forward to slide 21. So got the machine put together, and then working with Dr. Klaber, we just started making a lot of different types of chars and looking at them. Dr. Klaber can go down to the synchrotron down in the Livermore National Laboratory, and he ran many XRD scans. And we found significant differences between all these different chars that I was making. Next slide, slide 22. So our initial data, you can see that there was huge pH differences. There was different signals that we saw from the XRD observations. This is just a graphic illustration of all chars are not created equal. These chars are all going to have different values in the ecosystem for use, right? One char isn't necessarily better than another. You have to find out where those chars are valuable and where they can do services and have value that can be returned. So next slide. The screening of the material is very, very important. When we look at these different, you can see the XRD scans just physically and structurally, there are different materials, and we're not even talking about the chemistries. So that's going to result in different types of molecular sieve activity beyond even the reaction of the material itself. Next slide, slide 24. So we can kind of skip this, and we're going to move into the water quality aspects that we started to investigate. So the water quality, like, it's a triage situation, really, right? We've got to redo. We've got a very finite amount of water. And we have impacted it as humans in multitudes of ways in almost every place that we touch, right? And now we have an opportunity to start to clean this stuff up, and to kind of reset and get out of triage and get into stabilization is where I'm trying to get. So as we move into the urban infrastructure, next slide, water is really one of our most valuable resources, right? And so as we look at what happens when it hits the urban infrastructure, well, we create turbidity, we add metals and inorganic toxins. You guys all know the story. So we started investigating water cleanup, because quite honestly, it was a place to start that maybe had economic value. It's kind of hard to sell biochar to farmers at an economic rate that makes sense, especially early, right? We're talking about, this was in like 2010, 2011, something like that. So I worked with Dr. Klaber and one of his grad students, Miles Gray, and we got a grant. We're on slide 27. We got a grant in 2014 at Sweet Home from the Forest Service to look at their wastewater treatment plant. And I made 15 different char combinations. These were medias that were the char that we made was then just mixed with various components. And if you look at the results, you know, we came up with, you know, being able to look at metals, being able to look at nutrients, and the different chars had vastly different, or the different char mixes had vastly different results. And but we saw some things from this. So when we added, when you look at, I guess it would be the selection number 2, it was 25% compost, and we had really excellent results with metals. We did push some nutrients out though, and so we went back, and that's when we started looking at, you know, what was the compost adding, and we started thinking about organic acid functionality. And that ended up leading to work that we're doing now, and what I mentioned about the peat earlier. We're using the peat. We're using a particular kind of peat that doesn't really lose the nutrients to the system. But that's what led to, you know, next step was just looking at raw data and kind of learning like a monkey. Next slide. So I designed with Miles a way to capture the metals off of the roofs. A lot of the metals in the urban infrastructure is coming off the roofs, off of air handling equipment, off of metal roofing that sits out in the sun, builds up metal oxides, and then when the water comes, it flushes it off. So this system is an upflow filter. The top of the filter is basically a way to take the surges of the stormwater and also to detent and take out a great deal of the sediment before the bottom filter, and then flows up through the media and then out the top of the bottom filter. The flowing up through the media of the bottom allows us to avoid channeling in the filtration media, so we get complete saturation of the bed, and we don't get flows through channels through the media that makes the media less effective. And it's a very important thing. There's 2 things about using biochar medias in these stormwater situations. One is knowing what your flow rates is, so that you can predict how much water you can take in it. And the other thing is you really have to get rid of the fines. The fines, if you have below basically about a 100 mesh screen, is what we found, but if you have 10% of your media below 100 mesh screen, you're going to blind out. We ended up adjusting higher than that because over time we saw that we were losing some of our flow rates, so we ended up getting a little bit more coarse material that we developed, a way to get the fines out. I have a closed loop kind of washing system that we do to clean the fines from the system. Go to the next slide of slide 29, and you can kind of see some of the data. So the first project that we did this at kind of a scale was up in Port Townsend, and so this was in 2014, and we had we were taking up huge amounts of copper, huge amounts of zinc, which was their primary issues. We had a reduction of 93% of the zinc that they had in their facilities coming off of their hardscapes, basically. And that was running through this biochar and organic acid donor combination. We continue to do that work. I have some clients that I sell the material to. I build some of these totes. I don't really get involved in, I guess, too much of the marketing, right? I'm more interested in product development. And it's exciting to me when we see these results. And so now we're deploying these filtration systems up and down the West Coast. My clients that I work with are, and they've been having really excellent results, you know, and I want to make it better all the time, but these guys are deploying it. They're having return customers, you know, that's pretty exciting. So that part's been going on, and that's specifically around dissolved metals. And the next slide, we look at, we're on slide 30. We started doing work with Herrera Engineering up in Washington State while they were developing their new LID manual. And this work began 5-6 years ago. And basically, I started supplying them the chars that I was using, just the raw char, and Curtis Hinman put them into various mixes, and our char kept coming out as one of the key components of the mixes that they were testing. So that now, the work that Curtis and Herrera did is now, like I mentioned earlier, it's in a draft out in the state of Washington for basically the state of Washington's specifications for their new bioretention media has char as part of that specification. So that's pretty, I think, for the biochar community as a whole. You know, as long as you can meet the specifications, you could maybe supply, you know, whoever needs it in the state of Washington, you know, and that's great. That's what we need. We need specifications for it. So as we move into the next slide, what does char do for us in the urban environment? Well, as we all know, it can help plant establishment. The urban soils are hammered. They don't support plant health very well, particularly if you go in and excavate within a swale and then try to plant a plant in it, it doesn't grow. So it certainly helps with plant establishment. With a pollutant capture, we've seen total suspended solids, COD, heavy metals, hydrocarbons. All of those we've done work on. The pesticides and herbicides, that hasn't been really looked at very much. We don't have a lot of testing data from real world experience. We do know from the lab work that it does help with many pesticides and many herbicides. And then certainly what Chuck was talking about earlier with infiltration to get water just to go into the ground, right? It helps with infiltration to a great degree. There's a lot of good work that came out of and continues to come out of the University of Delaware around this. And it's very important for our stormwater managers on the municipal side. They like to get the water into the ground, and char helps significantly with that. Next slide. What are these mechanisms? You know, the mechanisms are various. You know, when we first started doing our column work with the raw char, we had a really good metal uptake for about 200 column volumes, and then it dropped off significantly. When we added the organic functionality of either a compost or certain peat products at about 20% or so, all of a sudden our column went from 200 to 2,000, right? And we started to think, what are the mechanisms? What's the change? Well, I think that the mechanism is changing over time. At first, it's probably an alkali-based crystallization. You know, you're pulling waters based on alkalinity. Well, that alkalinity gets lost, right? And after that alkalinity is lost, that alkaline functionality of pulling metals out of solution, something else took over. And that functionality is these organic acids that are getting put into the matrix of the biochar structure. So the next slide, slide 33. These are some projects that we worked on. You know, just getting char into the ground, and we're showing values with heavy metals, nutrients, hydrocarbons. Like I said before, there's huge amount within the infrastructure of the urban environment, you know, we have green roofs, green streets, rain gardens, stormwater swales. All of these things benefit from biochar becoming part of that system. Next slide. Slide 34. That's just some more kind of projects. The one on the right there, figure 1, that's some of the work that Herrera did up in Bellingham that informed the state that the value that char brought to the situation that they were dealing with up there. And then this is not work I did, but it's just a demonstration of, you know, the great things that can do on roofs in the urban environment. And we've done some work here at OSU in some mesocosm roofs and saw good results. But this is something I think that needs to be exploited more by the biochar community and get more green roofs built. You know, it's a light material, holds on to water, holds on to nutrients. You know, it's kind of the thing that really a lot of green roofs need. And then if we move to the next slide, slide 36, I think Howard Sprouse talked about this work. We did this many years ago, and we had fantastic results with cleaning up of PAHs. And this again is something else that we should hopefully get more work done now that, you know, kind of the capacity of the biochar community is built up, and we've got more trust from the engineers that they think we can supply them, because that's been a big problem from the engineering perspective, is that they were getting different material at the time and they weren't able to get enough consistent supply. Well, we've matured, I think, as an industry, and we can start to look at something like this. Like this is, you know, in situ remediation in a harbor as opposed to dredging, right? You can imagine the value of that to the environment. So the next slide is kind of the end of it, and that's just my contact information and my original machine. And with that, I guess I'll leave it.